The next video is a continuation of how to solve exponential equations. I think you'll find that these are a little bit more challenging. They got a little bit more variety to them. So in 5a, we're looking at solving an exponential equation. It's really important that you start identifying what you're solving. It's an exponential equation because in your exponents you have variables. So to get your variables out of the exponent, PEMDAS backwards, there's nothing that we can do here. There's no adding, subtracting, or multiplying, dividing that we can do. Everything that needs to be taken care of is in the exponent. So what we're going to do to undo exponents is what we've learned, and that is use logarithms. Again, I'm going to choose to use natural logarithm because it's a little shorter to write. That's really the only determination that I'm using. So the natural log of 5 to the negative x plus 1. Okay? The reason we want logarithms is that we can use our power rules and we can get our powers, our exponents, we can bring them down as coefficients. So now it's also important, if you notice I put that in parentheses, this was the exponent. This exponent is a single argument or a single value that we need to keep intact. So it's 2x plus 4 times the natural log of 6 has to equal, and the same thing over here, this exponent has to stay intact, negative x plus 1, so that power times the natural log of 5. Well, part of our dilemma is we have x's on two different sides of the equation, and eventually we want to get them on the same side. But before we can do that, we have to distribute this really awkward or unusual thing called the natural log of 6 and the natural log of 5. So in order to get our x's eventually collected, we first have to distribute our natural log of 6 and our natural log of 5 to get two expressions with just x in them. So here's what it looks like. You got 2x times the natural log of 6, and then you got 4 times, or plus, 4 times the natural log of 6 equals, and this is the natural log of 5 times negative x, or negative x times the natural log of 5. And then we've got plus, if we distribute the natural log of 5 to 1, just the natural log of 5. It's kind of hard to see this, but the natural log of 6 and the natural log of 5, wherever they are, they're just constants. Remember, it is the exponent you raise e to get 6. It'll be a constant number. So this is a constant, this is a constant, and these are constants. So what we want to do is, anytime we have linear equations, and that's what we're down to now, we're down to a linear equation, we'd like to get the terms with the x's on the same side. So I want to get this negative x, that times the natural log of 5, over here with the other expression that has a value of x in it. So we got 2 times x, natural log of 6. We're going to add on to it an x times the natural log of 5. So now I've got the terms with the x's on the same side. In the same step, I want to move the things that don't have x's away. So equals the natural log of 5. And now I'm moving this plus 4 natural log of 6, so I got to subtract 4 natural log of 6. Now we've encountered these many times before. We have an x in two different terms. The way that we get it down so that we can get just one representation of x is to factor out the x. If we factor out an x out of each term, then we got 2 times the natural log of 6 plus the natural log of 5 equals, and then you got the natural log of 5 minus 4 times the natural log of 6. If I want to get x by itself, then we want to do the inverse of multiplying by this expression, which is a constant. It's just an ugly constant, so x equals, here we got the natural log of 5 minus 4 times the natural log of 6 divided by 2 natural log of 6 plus the natural log of 5. Now we can find the value of this expression by punching those values in our calculator, and then I'm going to come back and show you what the book is showing as another alternative to this as well. I want to clear that mark off of there first. Hopefully it allows me to do that. Okay, so here's what we're going to calculate. If you're going to do it all in one, make sure you get plenty of parentheses in there, because I've got to take the numerator, which has the natural log of 5 in it. So natural log of 5, and as soon as I hit natural log, there's a parenthesis. I got to close it because 5 is my argument, minus 4 times the natural log of 6. So 6 is the end of the argument, so close that with a parenthesis. Now that's the end of the numerator, so I close that with a parenthesis. I want to take that numerator divided by the denominator. So the denominator needs to be encapsulated in parentheses as well. 2 times the natural log of 6, close your parenthesis on the argument of 6. Then you take plus the natural log of 5. Close that because that's the end of your denominator. Enter. And our answer is approximately negative 1.07. I'll be right back. These is paused. Okay, I don't know if I've ever told you how much I hate that stupid fan air exchanger, but that's what I had to do. I had to turn that off because it's starting to take off again. So our approximate answer then would be x equals a negative 1.07. So x is approximately equal to a negative 1.07. So that's what we're looking at. Now, I said the book's going to give you another option or outlook on this, and what they're going to do is they're going to take this and they're going to apply some of those logarithm properties. Right here, the log of a difference is the log of the quotient. So what we have is we have the natural log of 5 divided by 4. We can use a power property. That 4 can become 6 to the 4th, so 6 to the 4th, divided by, this is a power rule that we can use, so it's the natural log of 6 squared, which is 36, and since it's plus, let me take it a little bit slower. This is the first time through, so let me try to digest a little bit slower. It's the natural log of 5 minus, and it's going to be natural log of 6 to the 4th all over. Then it's going to be the natural log of 6 squared plus the natural log of 5. Okay, so then what they did is they go ahead and they apply a quotient rule and a product rule. So here's our quotient rule. The log of a quotient is the difference of the log. So I see the difference of the log, so I can write it as 5 divided by and 6 to the 4th power, and I can calculate that in a moment. Divided by the natural log of, so 6 squared is a little bit easier, 36, plus the natural log of 5, so anytime it's addition, it's the product rule, so times 5. So then what we can do is, I'm going to need a little assistance here. I got to take 6 to the 4th power, which is a 1,296, so this is the natural log of 5 over 1,296 over, and then a 36 times 5 is going to be the natural log of, and then a 36 times 5 is 180. So the book is going to convert that into this statement, and then eventually they go back and they convert it to a decimal anyway. So just to show you that you get the exact same values, whether you do the extra work of converting it using your power rules, quotient rules, product rules, or not. But it makes it a little bit easier to put in a calculator, I guess I would say that. So it's the natural log of, we got 5 divided by 1,296. We want to take that and we want to divide it by the natural log of 180, and we should get the exact same result we had before, negative 1.07. So showing you a couple different ways, and don't be surprised that the book shows you that this is what you get, and then they get a decimal approximation rather than where I stopped up here. I stopped here and I said, well, I can enter that in the calculator and get a result as well. So let's take a look at the second example they have for us here. We're going to do the exact same approach. There's no PEMDAS, there's nothing to do in our PEMDAS except get rid of those exponents, and we got to get their exponents out of there, so we're going to elicit the use of logarithms. So the natural log of 4 to the 3x plus 2 equals the natural log of 6 to the 2x minus 1. We're going to use our power rule. The power rule says the log of a power is the power times the log, so it's 3x plus 2. Make sure you keep that grouped. The natural log of 4 equals, then we got the grouping of 2x minus 1 times the natural log of 6. So you applying the power rule. Now we're going to use our distributive property. We're going to have to distribute, and we're going to have to eventually get our x's on the same side. So this is going to be 3x times the natural log of 4 plus 2 times the natural log of 4 equals, and this is going to be 2x times the natural log of 6 minus the natural log of 6. Now the only terms that have x's on them or in them are these two terms, so I want them on the same side, so I'm going to move them to the left side, so 3x times the natural log of 4, then minus 2x, the natural log of 6, and I'm also going to move at the same time to cut down the number of steps, the 2 natural log of 4, so it's a negative natural log of 6 minus 2 natural log of 4. Once we get to this stage, it's going to be a factoring stage. Factor out your x that's common to both terms, so x times 3 times the natural log of 4 minus 2 times the natural log of 6, and that equals your negative natural log of 6 minus 2 natural log of 4. We want to get rid of the division or the multiplication of this constant, so x equals, we're going to divide the left and the right side by 3 natural log of 4 minus 2 natural log of 6. Okay, and then I'll just kind of follow through with what I did the last time at the very end there. You can go ahead and calculate this as you have it, or if you want to, you can make this a negative natural log of, well, let me rewrite that too, because I don't want that negative sticking out in front of it. So it's the natural log of 6 to the negative 1 minus, and again, I guess I'll get rid of that one too, so plus the natural log of 4 to the negative 2. So I'm using the power rule there, over, and this is going to be the power rule, natural log of 4 cubed, plus the natural log of 6 to the negative 2. And then we can go ahead and use our product rule now. This is the natural log of, now it's going to be 6 to the negative 1 times 4 to the negative 2 over, and this is going to be the natural log of 4 cubed times 6 to the negative 2. And these things in themselves can be simplified. I'm not sure how much longer I'm going to persevere in this part of it, but 6 to the negative 1 is 1/6 times, and 4 to the negative 2 is 1 over 4 squared, or 1/16, and that's over. The natural log of 4 cubed is 64, times 6 to the negative 2 is 1/36. So then this could be written as, just going sideways here, the natural log of 1 over 6 times 16, so we'll grab 6 times 16, 6 times 16, oh, I don't want to have a marker on the end when I do that, so 6 times, okay, now I really messed things up by doing that, okay, 6 times 16 equals 96, so it's the natural log of 1 over 96 over the natural log of, and then I'm just going to write it 64/36. And that could be reduced. So that should be equivalent to our first statement. So punching that in, we got the natural log of 1 divided by 96, and barring any errors, this should be what we need, divided by the natural log of 64 divided by 36. Enter, and that'll give us something to compare to. That is to be a negative, approximately negative 7.93. So approximately a negative 7.93. Now that requires a little bit more work. I'm trying to convert it, and you can see that there might be some spots in there where you might stumble and make some errors. So I'm going to go back and check it off the original one I had here. I'm pretty confident that what I had at this stage here was accurate. So I'm going to go back and make absolutely certain that those two things are equivalent to each other. So this time I want to put a parenthesis. I got a negative sign, and then I got natural log of 6, close the argument, minus 2, natural log of 4, close the argument. We want to close that numerator, divided by, now I'm going to keep the denominator in parentheses. We got 3 times the natural log of 4, close the argument, minus 2 times the natural log of 6, close the argument, close the denominator, enter. Negative 7.93. I believe that is the same value that I had written down here prior to. So it requires more work to get it down here. The one reason I would like to see it done this way is it's going to create some more practice for you to get them here using your rules. Power, product, and quotient rule. Other than that, you can do the same calculations that we have in either method. So, like I said, these are going to be stepped up a little bit. Those are a little bit more difficult, take a little more concentration, effort. Make sure you stay organized, show your steps, but it really follows this PEMDAS backwards model very well.